London, and he's going to be talking about quantum aspects of a lambda positive universe.
Okay. Yeah, good job for making it this far. Good to meet you all. I just wanted to finish writing some important papers from the past, and then I'll start.
I think the microphone is not catching you.
Oh. ¿Cómo es? Hello?
Can you,
Yeah.
well, sorry. Like,
Oh.
Can you try to put it in your head, or is it too much?
No, yeah, I think probably it'll keep on falling. Well, if there's one thing you take out of these lectures, I would strongly encourage you to read these papers over here. Yeah. I'll mention papers as we go along. Now, yeah. Okay, so the topic that I'd like to discuss with you is the topic of quantum properties for theories of gravity endowed with a positive value for the cosmological constant. Okay? And I think it's good to motivate why and to reflect a little bit as to why this is a topic that we should think about in the subject of theoretical physics. And so it seems appropriate to motivate the subject a little bit in the beginning. And so I'll do that. And while I do that, you should feel free to ask questions or provide comments. And I don't mind derailing at all into sub-topics or discussions if they so arise. Now, part of the motivation for studying this problem, goes back to the 20s, actually, the 1920s, where as people started to measure detailed properties from the light of distant galaxies and the patterns of redshifts and started collecting more and more information, people came to the rather remarkable conclusion that the nature of space-time at very large scales, so scales that exceed the distance between multiple galaxies, millions of light years, that the structure of space-time on very large scales exhibits considerable time dependence. Okay? And this is a way to express the fact that the universe we live in is... Maybe we should... Okay. I guess that's the last batch. The universe we live in is a cosmological space-time, which means that the volume of space is a function of time. And ever since the 20s, all measurements people have made about distant objects in the sky have given supporting evidence for this picture. The picture, yeah. I have to put the microphone on my head? I'm sorry about these technical troubles. Okay. I find this very uncomfortable. But okay, anyways. It's a little too loud now. Sorry, yeah. Now, one thing that this feature of spacetime implies, okay, and I think it's important to say it in its most bare terms, this is something remarkable about spacetime, is that as space expands toward the future, it also means that it contracts towards the past. And as it contracts towards the past, one could exhibit situations where it contracts to a very, very small, highly dense phase. And we have to be sure that the laws of physics apply the way we understand them in an ordinary laboratory system, that the laws of physics apply for the universe at large, which means that this is a question about the deep infrared properties of space-time. So are we sure that the quantum mechanics or effective field theory applies to physics over cosmological scales that may even cut across regions of space-time that are accessible to any given observer? Yeah, and we'll come back to that. So that's a question of whether we have a good infrared or deep infrared description of space-time at the quantum level. And there's also a question, since space can contract and shrink and become dense, of whether we have a good understanding of the deep ultraviolet of a cosmological space-time, like the one we appear to reside in. Now, both of these questions are intimately connected to the necessity of a quantum description. In the ultraviolet case, perhaps it's more clear why this is so. But to add to this, you can take into account the kind of ideas and theories that Guy has been talking about, which is inflation, where you see quite clearly that in the early universe, quantum fluctuations of fields, and not just matter fields, but also gravitational fields, play an important role in the future development of the formation of galaxies. Yeah, so in the inflationary hypothesis, which is one way to discuss this phase of cosmology, you have a phase where you have fluctuating quantum fields, but also fluctuating gravitational fields. Yeah? And you have to be sure that the standard rules of quantum field theory and quantum gravity and effective field theory are applicable in this period of the universe. For instance, if inflation happens at a very high scale compared to some other scale, it could be of effective field theory, it could be a scale where higher dimensions kick in, one has to be sure that these effects are properly understood. That's the UV necessity for quantum features. Now you may wonder why you may also require quantum features in the deep infrared phase of cosmology. After all, isn't that where everything becomes low curvature, you know, macroscopic, and so forth? However, as we've learned from the theory of black holes, it's not always the case that the deep infrared is immune to quantum effects. And cosmology, cosmological spacetimes quite often exhibit their own versions of event horizons, which are tied to quantum questions in the infrared. And also, perhaps relatedly, or perhaps not, we have the observation that dates back to the 60s at least, actually maybe 1967, when Zeldovich observes that the value of the vacuum energy, so what is this lambda over here? This lambda is a type of vacuum energy that permeates throughout space-time. We'll discuss it in more detail in a moment. That this object, the cosmological constant, which is the leading, in Wilsonian terms, the most relevant operator in the effective field theory of gravity, receives unprotected quantum contributions from all fluctuating quantum fields in nature, okay? And so that it takes the value that it takes, which is 10 to the minus 122 times the Planck scale, yeah, in Planck units, is somewhat mysterious. Okay, so we've measured this thing. It appears to be constant, although more experiments need to happen to ensure that, but it appears to be constant, part of what's called the Lambda CDM model of cosmology. But why do all these contributions, which naively are sensitive to ultraviolet scales, why do they conspire to give a value that's so peculiarly small? And this is sometimes referred to as the cosmological constant problem, okay? So the dark energy, or the cosmological constant that drives the expansion of the current phase of our cosmology, is such that it receives quantum contributions from all vacuum fluctuations of fields, yes, and therefore is tied, especially given its peculiarly small value, to questions about quantum mechanics. Moreover, lambda is also the culprit behind the formation of cosmological event horizons. And so there seems to be something to be said about that, okay? So the point that I want to make, sort of as a way to motivate these lectures, is that the cosmology that we reside in, that we've been presented by measuring things for over 100 years, yeah, appears to require a quantum description if we're going to have a complete theory, a complete theoretical framework for our universe. Now, we know bits and pieces of this framework, but as it stands, we do not have a complete theory for quantum aspects of cosmology. In particular, this is tied to theoretical developments regarding the quantum nature of space-time, over the last 30 or so years, which indicate that the metric field, as we know it, in the underlying formulation of a theory of quantum gravity, may have to be replaced with a different set of degrees of freedom. Okay? So the most prominent example of this is known as the ADS-CFT correspondence. And in this correspondence, we replace a theory of gravity with a conformal field theory where there is no dynamical quantum metric field. Yeah? And if this paradigm, yeah, I don't know if you're familiar with ADS-CFT, I assume many of you are, but if this paradigm holds for spacetimes that are non-anti-de Sitter space, including cosmological spacetimes, it suggests that we may have to find ways to replace the metric or standard effective field theory formulation of cosmology coupled to matter fields with some other underlying degrees of freedom. And they may dictate when precisely the breakdown of effective field theory occurs. Okay? So that, I think, at least for me, that's the stage. That's the stage on which we base these questions, and why I think it's a pressing problem to try and develop with modern tools of theoretical physics a more complete framework of cosmology at the quantum level. Okay? So that's roughly where these lectures are coming from. And like all problems we do in theoretical physics, it's important to find aspects of the questions that we're studying that are sufficiently universal, that we can isolate from the details in order to have a clearer understanding, much like we would if we're studying a black hole, where we, of course, a black hole in nature is a rotating curved black hole surrounded by an accretion disk inside of a galaxy in a very noisy environment, and that's a very interesting problem. It may be merging with another black hole. But once we identify that there's questions tied to the black hole that we need to understand in a theoretical sense, we try to isolate it and ask the question in its more idealized form. And similarly in cosmology, there's a very large class of cosmological spacetimes. In particular, this was already going back to the work of Alexander Friedman, I think it was 1922, where he wrote down a class of metrics under the hypothesis of homogeneity and isotropy. So these are type, what are known as FLRW type spacetimes, yeah? So you can say, at a coarse level, a metric associated to a cosmology, you could say, is related to this kind of a spacetime. And what you've done here is you've assumed that roughly, along sufficiently large scales, you've averaged out the small details and you've taken your spacetime to be homogeneous and isotropic, which means something very specific about this. Yeah? So this is a three-dimensional spatial metric, and there are three homogeneous and isotropic spaces, yeah, labeled by this parameter k, which can take the following three values, okay? And, well, does anyone want to take a guess as to what these three spaces are, just to make sure we've had our morning coffee? Don't be shy. I'll give you 17 seconds. Yes, but the Euclidean version, whoever said Minkowski. Yeah, so indeed. So it's the hyperbolic three space, the flat three space, and the round three sphere, yeah? So these are, and they all have constant curvature spacetimes, yeah? They're cosets. And so the idea was that, well, on very sufficiently large scales, perhaps the universe takes this form. And there's evidence for this, especially when you start probing the universe over 100 million light years or so, I think, when you start coarse graining. There is significant evidence, but also from the CMB, that this is a good hypothesis, homogeneity and isotropy, okay? And what it says, yeah, what it says is that we are not living in any special point inside of our universe, yeah? So what happened when Friedman writes this equation and tries to formulate, this is the first, if you want, one of the earliest equations in theoretical cosmology, and tries to formulate the idea that we're not living in any, you see, this is what it's saying, that we're not in an overdense or underdense region, that if there were observers in some other region, they would roughly see the same thing. And it's an important principle, because it, in a sense, is an attempt to dispense the theory of the observer. Now, as an aside, and somewhat ironically, in the 20s, roughly at the same time, people were formulating the Copenhagen interpretation of quantum mechanics, which was all about placing the observer into the theory in order to be able to make predictions out of the outputs of the equations. Interesting situation in the 20s, that you have cosmology trying to dispense itself of the observer and saying everything is the same everywhere, and quantum mechanics trying to make sense of the equations by putting in the measuring device and associating the wave function to probability. Fast forward 100 years later, most of the theories of quantum mechanics and quantum field theory formulated, we found a way to idealize the observer into an object that lives infinitely far away from the quantum dynamics we're interested in, be it the S matrix or correlation functions or whatnot. And in cosmology, it appears that we're entering a phase, this is an aside, where we're starting to grapple with the fact that we don't have access to this infinite universe, but rather we may have to have a more local description. So there's a historical irony here. And okay, so here, well, since I mentioned that, let me mention a homework problem, because I was instructed to give homework problems, just to give you a sense of the scales. Yeah? So let's do a quick calculation, and then I'll go back to the equation. Calculate the ratio, here's a fun exercise, of the size of the visible universe, which is roughly 20 billion light years, divided by the size of the largest telescope on Earth, about 500 meters. Okay, so it's exercise 1. And exercise 2, calculate the size of the ratio of the size of the Atlas detector to 10 TeV, which is the energy scale in units of distance, which is what the experiment probes. So this, you'll get two very large numbers, which are awkwardly close to each other. So that's your first homework problem. Yeah? And I think it's important in order for you to get a feel of the ratios of scale. So 20 billion light years divided by 500 meters is roughly, if I remember correctly, 10 to the 22 or so. And the size of the Atlas, about 50 meters, I don't know how big, order 10, 50 meters divided by 10 TeV scale is a similar order of magnitude, because 10 TeV, I have it written down. 10 TeV is 10 to the minus 19 meters, okay? But just for you to get a sense, because I think it's important that we have a sense of the scales that we're dealing with in this problem. So the size of us compared to the universe that we measure by locally collecting light, processing it, and deducing the large-scale structure of the universe is parallel to being a 10 TeV size object, collecting time and deducing the structure of the Atlas detector. Those are the scales that we're talking about, yeah? Just so you have in mind the scales that we're dealing with. Okay, back to FLRW. Friedman, Lemaitre, Robertson, Walker. So this is perhaps the first expression of what it means to be a cosmology, and A of t over here is a function of time that's determined by the type of matter fields and equation of state that's present. So this is what you feed into the Einstein's equations, yeah? And what it was discovered is that the Einstein equations, in the presence of a matter stress energy tensor that takes the form of a perfect fluid, yeah? So you have some stress energy tensor which has the following form, and you assume you're in a frame where everything is equilibrated, average, and purely time dependent, aside from, so the metric over here. So you have the energy density, and then you have the pressure, and you allow them to depend on time, yeah? So the question was, given this assumption that there's some fluid permeating throughout space, what kind of solutions, and you assume this ansatz for the metric, yeah? What kind of cosmological solutions does one find, okay? So this is translated more succinctly. If you study the Einstein equations and you impose these symmetries and this ansatz, what you will find are these remarkably simple equations. I don't know if you saw them previously, but I'll remind you of them. And I'm working in 3 space-time dimensions for the time being, because that seems like a reasonable thing to do. And you get essentially that it boils down, and let me write the other one in a way that people don't often write it. I know. Yeah, let me write it like this. Yeah, now I'm happy. So you end up with the following 2 equations, okay? Good. So one equation is essentially equivalent to the conservation of the stress energy tensor, the first FLRW equation. And the other one over here, you can sort of view as a statement that in gravity, all energies have to vanish because of the Hamiltonian constraint of general relativity. Yeah? So gravity has this curious feature that time translations are themselves part of the diffeomorphism group and therefore pure gauge. And in being pure gauge, it means that there has to be a constraint associated to what they generate, in particular the Hamiltonian, which is the generator of time transformations. And this expresses this fact. Yeah? So you can view this as a kinetic piece of the metric with the wrong sign compared to the standard positive kinetic term. Yeah? Plus the energy density, which comes from two sources. One is from the fluid itself, rho, yeah? And the other is a contribution to the potential energy carried in the system that comes from the curvature term. And it all adds up to 0. So one way to think about this equation is to think about it as the fact that energy vanishes in GR. And the way that GR accomplishes this, how can the moon have 0 energy? The way that GR accomplishes this is that it can contribute negative terms. The kinetic terms of the gravitational field can contribute negatively. Yeah? So that's the catch. Without the system being unstable. Okay. So now if we wish to solve these equations, so now the name of the game is clear, because then what one wishes to do is to solve, given an equation of state, given a particular fluid. Yeah? So for simplicity, one can assume something like an energy density proportional to the pressure. This would happen, for instance, if you had featureless dust, which is pressureless. In that case, W would be 0. If you had radiation, something like this would happen as well. Or if you have a cosmological constant, which you can view as contributing to rho, which would correspond to the case W is -1. Or you could have combinations. Yeah? So what we typically do in our own world is we assume that this rho has different components, a radiation component with some percentage of the energy budget of the universe, a non-relativistic dust matter component, and also a cosmological constant component. And each of them affect this particular function over here. Yeah? Okay? So now, we can ask, if they're all present in the initial state, the initial fluid, some time t equals t naught, that drives the expansion, yeah? So then we'll have a rho that takes the following form. Let me write it in the way that cosmologists like to write these things, so that we learn a little bit of their language along the way. So these omegas are numbers. A is the value of naught is the value of the scale factor at t naught, some initial state. And this is the component of radiation. Notice that it dilutes like a to the 4th, yeah? So relativistic fluid dilutes like 1 over a to the 4th, yeah? So this is a nice calculation. So put a box, yeah, full of electromagnetic radiation and change the size of the box and measure how the energy density changes as a function of the volume of the box. This is dust, and it goes like 1 over a cubed, yeah, so it's the volume. It dilutes like the volume, because it's non-relativistic. And this over here, 1, expresses the fact that lambda itself, the source from the cosmological constant, is non-diluting, which is quite peculiar. There exists a source of energy in nature that drives the behavior of the metric as a function of time that does not dilute. If it does not dilute and A increases with time, it invariably will dominate the dynamics at sufficiently large values of A. Yeah? And so there's a clear sense in which this is a type of attractor behavior of cosmology, if it's present at all. Yeah? Because whilst all other forms of energy dilute that we know of in nature, the cosmological dark energy persists. And so it's an interesting, then, problem as a theorist, as a theory problem, to identify a universal piece of cosmology. This is what I was saying a few moments ago. And what we see here is that cosmology exhibits certain attractor behaviors. Now, it could be that there's some principle of physics, unbeknownst to us, that forbids such a term. Yes? But such physics would not obey the standard rules of low-energy effective field theory. Because this source over here, from the point of view of a Lagrangian formulation of gravity, appears in a very simple way. Yeah, so if you have some effective theory of gravity coupled to matter, yeah, all this term does is turn on a coupling constant for this covariant piece over here. It respects the symmetries of the Lagrangian, it's gauge invariant, yes, and it's the most relevant term in the Lagrangian. In other words, it is the term that dictates influences the dynamics on the largest distance and time scales conceivable. Okay, and you can have matter here as well. But it could be that for some reason, some quantum mechanical or beyond effective field theory reason, there's such a term is not present, but we have no clear principle to exclude it at this stage. And so there I would suggest very much, encourage you wholeheartedly to read this paper of Weinberg, which is an overview and much more of the cosmological constant, where he anticipates that we should probably measure such a thing. And of course, the value that we measure has to be compatible with all the other properties of science, galaxy that we already observe. And so he anticipates that if we measure it, it cannot be too large, and quite remarkably points out the value at which we ought to measure it, which saturates how large it could be if we kept everything else fixed. Yeah, very interesting idea. Fantastic paper. Please read it. No excuse. Okay, so this effective field theory reasoning is in a sense reflected in this FRW type equations, in that indeed for large enough scale factor in the most infrared phase of cosmology, this dominates the equations. This thing, I should say, this is a constant, yeah? And this over here dominates the physics. And so we have, as a theorist, it's interesting to find universal attractor behavior. This is a little like in quantum field theory, where we try to study the fixed point, yes, of an RG flow and try to control the properties of this fixed point. In cosmology, we have these kind of attractor behaviors as well. And so this drives us a little bit in trying to formulate theory questions to see if we can, at least as an idealized version of the problems I discussed in the beginning, which are problems that have to do with cosmology at large, not just about the de Sitter or some other solution, at large, whether we are driven to this value and we can try to study its properties. Yes, as an idealized version of the broader questions we'd like to understand in cosmology. Now, by good fortune, it so happens, not only do we have evidence in the present phase of the cosmology that there appears to be something like lambda, although future experiments will help us make that statement sharper, including the DESI experiment and the Euclid spacecraft experiment. So in the next 5 to 10 years, we're going to collect data from the 100 million galaxies to deduce as clearly as possible whether lambda is truly constant, which so far all evidence is compatible with that statement. Not only is that the case, so that's a phenomenological point, but the early universe, at least many prominent theoretical descriptions of the early universe, seem to have, so this goes by the name of the inflation theory or the inflation hypothesis, a phase of the early universe that is also approximately of this type. Because you see, if I had matter fields in my theory, imagine for simplicity, I had some scalar field as well. Yeah. So I had some scalar field as well with some potential. So imagine that there was some scalar field. We have scalar fields in the standard model. There could be other scalar fields in the early universe that are activated. String theory, as an example of a more complete theory, has full of scalar fields. So imagine there's some scalar field. And you have some potential, V of phi, yeah, which has some features. Yeah, there could be regimes in which the potential has minima, in which case we're back to lambda with fields fluctuating. But there also could be regimes where it has unusually prolonged, almost flat behavior, where you can have something like a slowly rolling universe, where you don't quite have a pure lambda universe, but something that is fairly approximate to that. And in fact, we appear to be in a situation in inflation where if you squint your eyes a little bit, it appears that a lot of the physics of the lambda constant universe apply to the way we develop the theoretical formulation of inflation itself, which I believe you've heard about from the Guy's lectures. Yes? And there's parameters that quantify how close you are to that. I don't know if he called them the epsilon eta parameters, but there's parameters that control how close you are to that. And there's parameters that quantify how long that period lasts, which since you have a scale, you can talk about how long it lasts in terms of a number, a dimensionless number. Dimensionless numbers are always our friends, okay, which is the number of E-folds, which is how many lifetimes has this universe had in units of its characteristic scale lambda. And what we know about inflation, at least in the simplest models, is that there's an upper bound, there's a lower bound on the number of E-folds, which is roughly 60, which if you have a world that's growing exponentially is 10 to the, e to the 60, or e to the 60 times 3 volume, yeah? But we know of no lower bound, no upper bound on the number of E-folds during inflation. The other way around, yeah. It has to be, so it could be infinite. It could be a very, very large number. So our current understanding of inflation a priori could have a period that lasts 100, 200, 400,000, 317 E-folds, okay? And so this is, again, going back to the question of the deep infrared, because there's also the question of, what about the deep infrared of the early universe before we exit, tied to the Olympics, okay? So there's this question also. Yeah, so these are parameters that we're measuring that tie to these bigger questions. Are there any questions at this point? Let's have a healthy, awkward silence. Get the adrenaline going. Yeah. Please. Is there a microphone? Yeah, that's a good idea.
Hi.
Hi.
A naive question about the density for cosmological constant. You said it was not diluted, right?
Not diluted.
Yes. So that means the lambda parameter is like constant in time or something like that?
So here, indeed, so when I say this, I'm assuming a theory where this lambda over here is constant, and it being constant is compatible with all of the rules we know of effective field theory and general covariance. Yeah.
I have read maybe somewhere like strings, I don't know, like maybe some weird investigation, I don't know, that maybe lambda it's also time dependent.
Yes, yes,
something like
indeed. So I was trying to emphasize that,
Okay.
that it could be that there's some principle that forbids the existence of a lambda constant, but this principle would be beyond the standard principles used in low energy effective field theory, and we don't know any theoretical reason from first principles why this would be the case. Tied to this, though, I should say, but many people are investigating such a thing, and it's a priori not disallowed, because inflation, in a sense, you could view as a slowly rolling lambda. Now, what I can say to that is that often, if it is time dependent, one model to do that is to have a field that is rolling. But when you have a field that's slowly rolling, it's a very light field, and so it has fluctuations that could influence physics over large distance scales. And we haven't seen any such field in the current universe, analogous to the inflation field in the early universe. And that would be one way to get a hint. Nonetheless, there are experiments that are trying to measure any potential such time dependence. But so far, the experiments are compatible with a constant. Yeah,
Thank you.
Very good question. Thank you. More questions? We have two over here.
Sorry, in this kind of models, you always consider 3 ingredients. There is a reason to consider 3 ingredients, not more than that? Cosmological constant, radiation, and dust.
It's minimalistic, and it agrees with the experiments. And when you have a perfect fluid formulation, this seems to cover the cases that we know based on the matter content that we've observed in the lab. So it would be very interesting to propose more exotic contributions to the density of state and see what their impact is. But so far, this complies with many, many constraints that come from cosmological evolution. So if we add more parameters, it's usually should have a good reason to do so. Yeah, so this is minimalistic, but it's compatible with our other understanding of physics and agrees with the data. Yeah.
Yes, you mentioned that there are going to be a lot of information for measures in order to see that if it's truly constant or not, the cosmological constant. And I remember from my gravity course that was the last time I saw a data of the cosmological constant, that it is measured and is almost aesthetically Minkowski. So I wonder if it is a close discussion, if this is the sitter, or it still can be like the cosmological constant is almost zero or something.
So this, you see, here is my rule. That's not a dimensionless statement. Almost zero for a dimension-full parameter doesn't mean anything. Compared to what? It's, for instance, it's sufficiently non-zero that we can measure it. If that's the condition that it's meaningful, then okay. Of course, if we're doing physics in the LHC, in units of those things, it's effectively zero. Yeah? So we can ignore it for that. But it depends on what we're after. And here, the emphasis is on the cosmological scales. And this sets the units, in a sense, for those scales. So the order of this parameter, just to give you a flavor, so lambda, maybe I should give you numbers. Lambda has units of 1 over length squared, and it's measured to be 10 to the minus 52 meter to the minus 2. Yeah? Okay? So small or big depends. It's measurable. And it dictates the large-scale structure of our world. Yeah, so the redshift of light from galaxies, distant galaxies and supernova are sensitive to this parameter. Yeah. But was there another question? Okay. If not, and I wanted to give you another one, another number, because I think it's important that we also connect a little bit with the actual numbers, which is that rho, the energy density of the current world, which 70% of it, another dimensionless number, is what is all of the energy sources in the visible universe, what percentage is coming from lambda? And it's 70%. So that point of view, it's difficult to ignore. Yeah. But the energy density is, I think, 10 to the minus 27 kilograms per meter cubed associated to it. That's another calculation. Because the energy density is lambda over g. So you have to compute lambda over g. G is the Planck length squared, yeah, and convert it into a density. Yeah, that's another one. Let me see that I got it right, because sometimes I remember things incorrectly. Yes. 10 to the minus 27 kilograms per meter cubed. These are the numbers. Okay.
Dio, sorry, one question. Here.
Ah.
Can you explain, if it's not fast, we can discuss it later. Can you refresh to me how is this 70% number built?
So this number is built by measuring the redshift patterns of at different values of the redshift. The redshift has to do with the frequency of light emitted during its emission and how we measure it, which is sensitive to A. And based on the redshift patterns that we measure, we can deduce A of t by solving these equations. And so these equations predict an A of t that is sensitive to omega lambda, omega radiation, and omega dust. And if we compare this to the measurement of A of t, and we do a fit, this will fit only for certain values of these parameters. Yeah? So that's one way. Another way is from the CMB.
Sorry, because they depend differently on A. That's
of course.
Okay,
so then it'll give you a different, you see, if I tune these differently and I solve these equations, I'll get A, the function of t will be sensitive to that. Yeah. Yeah?
Great, thanks.
Yeah. Also, but there's other indirect measurements that agree, which for instance, for the CMB, can also measure the value of lambda. But anyways, this is the most rudimentary, the most pedestrian answer to the question. Okay, good. So that's where we're at. And I'll re-emphasize that as it stands, and especially based on the kind of developments that we've seen in the context of black hole, the theory of black hole physics, we don't currently have a complete mathematical formulation of cosmology at the quantum level, even though we've known that we reside in one for over 100 years. Pressing question. Okay. Maybe more timescales, though. Lambda was first measured in 1998. It was announced by groups measuring supernova experiments. So just to give you a sense of that, is a much more recent result. Yeah? So it's not an ancient problem. But from effective field theory, it's a very natural problem. All right, so now let's move on to the topics. So the goal, like I said, I'm going to keep it in this style of discussion because I think it's effective. And if it's not effective, you can give me feedback during the lunch or whatever. But what I would like to do is discuss, therefore, some of the properties of this attractor behavior of cosmology, yeah? So we're going to discuss features. So that's the reason why, okay, so hopefully at least we've justified the title, yeah? Quantum aspects of a lambda positive universe. Every word means something. All right. Okay, so what I want to do now is start to discuss the idealized version of this, where we are in the phase now where everything is dominated purely by lambda. Because it turns out that even that idealization is still a very rich physical theory at the classical level and at the quantum level. Yeah? And so the target, as a warm-up to the broader questions, is to study that problem. And I want to give you a bit of a flavor of this problem. Yeah? Okay. Now let me organize my thoughts. Let's do one more FRW calculation, because I want to stay with the theme, and then we'll move on to the sitter. So the other calculation I wanted to do has to do with the concept of cosmological horizons. So let's do one more sort of mini calculation. We can start it here and do it in the homework. What's the homework? When is the homework? What's the homework? In the afternoon? How many hours do just these are important. Just solve these problems. Okay, so here's the question. The question is, what is the condition on A of t, the function A of t, such that the passed light cone of an inertial observer cannot access the full causal structure of the space-time? Yeah, short question. And I guess the homework problem will be to show that this, assuming a smooth monotonic, you can assume that A of t is a smooth monotonic function, growing. If my memory serves me right. So that this is equivalent to the following condition over here. That if A of t satisfies this, there will be regions of space-time that are forever out of causal contact with the passed light cone of an eternal inertial observer. Now, the reason I emphasize this point, which means that the portion of the Penrose diagram close to this takes the following form. Yeah? So there's events here that are never part of the passed light cone, never part of the experience. The reason I emphasize this is that people in the literature, sometimes you see these cosmological horizons tied to the de Sitter. But this equation is more general than that. Yeah? And it's important to bear this in mind, that these features are not just about the de Sitter. On the other hand, if you put in the dust or the radiation, so let me remember, A of t for a purely dust universe, let me not try, I think it's the square root of t, but let me not try to reproduce it in my mind. Where is this? Ah, yeah. Radiation is the square root of t. So it grows, but as the square root of t. Dust, I think is, what was it? T to the 2/3. Purely, so interestingly, if we have no energy density at all, but we have curvature, this equation can have non-trivial solutions as well. Yeah? So this is a solution to the empty Einstein's equation. It's known as the Milne universe. Sorry. So it's a hyperbolic slicing, a time-dependent hyperbolic spatial slicing of Minkowski, and it has t equal, A of t equal to t, yeah? So all of these violate this condition. However, anything that goes just above the Milne behavior will generate this. Yeah, so a sufficiently accelerated expansion, not exponential. Of course, exponential would do this as well, yeah, because their A of t is e to the 2t. But you don't need it to be exponential. Okay, yeah, so cosmology and horizons are intimately tied with each other. And now let's do one final FRW calculation. So now let's take rho is equal to a constant. Yeah? And let's take rho is equal to minus p. So that's this cosmological constant equation of state. So then what happens? Well, we solve this equation for free. Yeah? And now let's take the curvature to vanish for the sake of simplicity. We don't have to. And now we have an equation, yeah, which is A dot over A is equal to a constant. Okay? So this equation is solved by A going like e to the t over some characteristic scale L, which is related to lambda, yeah? So lambda in 4 dimensions will be 3 over L squared. And so now we have our FLRW metric for a purely constant energy density in the spatial slicing. And we get the following metric, yeah? Okay, and what it is, so where x over here is a point on R3, yeah. Very good. And L is this characteristic scale associated to this parameter of nature. And T is the clock of an inertial observer sitting at a constant point, for instance, the origin, yeah? Measuring. And clearly, this very fastly growing space-time, yeah, obeys this condition, indeed. Yeah. So this one is the lambda, purely lambda-driven cosmology. Okay? Okay. So with that, I'm happy with my FRW intro. Now, are there questions? Comments? How are we doing for time? Sorry? It has been, or? Okay, then. Very good. Okay. I'm going at just the right pace. Now, so now the goal from now on, so you've had your chance to resist, but from now on, we're going to this attractor phase of cosmology, and we're going to discuss these features. And my goal is to give you a flavor of this space-time or its more general sort of geometric picture. And we'll discuss some classical features, and then we'll discuss some properties of quantum field theory because it'll be useful. And then I'd like to discuss, hopefully, what's known, some of the few things that are known about quantum features of gravity in this, which is the real open problem in theoretical physics. Yeah? This one is also quite open question, how to properly formulate quantum field theory in the space-time, but there's a lot of development. Nice subject. This one remains a big task that we need to accomplish. But to get a hold of the problem, I think it's important to discuss, well, what does it look like in its purest form, and what are its classical properties? And it turns out to even be a classically very rich problem. Okay. So like I said, we'll consider a class of Lorentzian theories governed by the following effective field theories, whose Lorentzian dynamics have the following flavor. Yeah, and we'll assume that our matter, if they're scalars in our matter field theory, they'll have well-defined positive minima, okay, so that our dynamics is not disrupted by any slowly rolling or anything like that. A priori, there can be all the standard couplings of effective field theory that there would be in a theory of nature. We have no reason to truncate the theory there, but to leading order, we will assume that there's a hierarchy between these different scales, and so these other contributions will be subdominant compared to the ordinary Einstein-Lagrangian for the time being. Always bearing in mind this is an effective field theory. Okay? And we would like to know what is the most symmetric configuration in the classical theory of this model. Well, what does that mean? We would like to, maybe we should place our matter fields in their vacuum state, which is classically vanishing stress energy. We're assuming that we have order 1 matter fields so that they don't give rise to cumulative quantum effects due to a Casimir energy or whatnot. And so we're tasked with solving the following equations, which are the Einstein's equations in the presence of a cosmological, I have to stick to my convention, of a cosmological constant, yeah. Of course, there's the matter equations as well, but like I said, for the time being, we'll keep these deactivated, and we'll turn them on gently once we understand the nature of the most symmetric configuration. Yeah? And the solution will, in fact, be robust to small effective field theory corrections in our classical theory of gravity by virtue of the large number of symmetries that it possesses. And so even though it's a time-dependent solution that we will find in this theory for all the reasons that we discussed, we can ask whether there exists a maximally symmetric solution to these equations. And a maximally symmetric solution is a solution that permits the largest number of killing vector fields, which would be 10 in 4 dimensions. And indeed, there does exist such a solution. And well, let's do a little exercise. Just by virtue of the equations that it satisfies, we can say that the matterless solution will have a particular value for the Ricci scalar. So what is this value? So take 15 seconds to compute it. Hopefully I've done this correctly. Yeah. Any takers? Sorry? Very good, 4 lambda, thank you. Do the units work? What are the units of R? 1 over length squared, units of lambda, check, positive, check. Okay, 4 lambda. So this is a solution that has constant, pointwise constant Ricci scalar. Yeah, it's positively curved space-time. And the solution in its most sort of geodesically complete form takes the following structure. I'm going to work with dimensionless coordinates so it takes the following FLRW form, yeah? This is known as the global de Sitter solution, okay? And notice that, remarkably, this solution has a bounce because the size of the 3-sphere, this hyperbolic cosine, it is non-monotonic. So this is actually an example of a bouncing universe. Now, we only have evidence of an expanding portion, and in fact, we don't have evidence that the spatial curvature of our world is curved at all, yeah? But that, in fact, is a matter of what the natural cosmological clock is for this space-time, because the theory, there exist patches that cosmologists like much more that are equally symmetric and really related by coordinate transformation. So this T, maybe let me call it T tilde. There also exists this slicing of de Sitter. So these are the same metric, but with different choices for the coordinates, yeah? So this is called a flat slicing. But it doesn't end there. One also has, well, please understand this T is a different coordinate in each. I hope that's okay. One also has, and let me be consistent with my coordinates. A hyperbolic slicing, like the Mellon universe. Yeah? Okay? So we have all three of our isotropic and homogeneous slicings, and 2 of the 3 have a monotonic scale factor, which is either sinh, yeah, or pure exponential, and one of them is a bounce. Was there a question? Oh, yeah. Yeah.
Working? Yeah. Sorry. Each of these metrics are the only solution for each of the, like, the sphere, the plane, and the...
Oh, no, not at all. We'll come back to that. Of course, this is the most symmetric solution, but this equation admits an enormous number of solutions, and many others are known, and we will discuss those as well. We will discuss their asymptotic structure.
Okay.
No. This is a rich dynamical problem, so generally it'll have many solutions. However, there is a sense in which all the or a large portion of the solutions at late enough times look like one of these. Effectively, yeah. locally look like this. And that's called the cosmic no-hair conjecture, which says that no matter what you start with, under some conditions about having a little bit of expansion, at late enough times, if you only measure physics in a finite proper volume, your physics will look indistinguishable to leading order from the pure de Sitter solution. Yeah?
Okay.
Good.
Thank you.
So that's a conjecture that has not been proven, but there's a lot of evidence for it. That's a nice target for the classical theory. Was there another question? Okay, very good. So this is the hyperbolic slicing. And also important is to appreciate that this, given the large, well, maybe it's actually a gift, that given the large number of symmetries, there's an embedding space perspective of this space-time, where you can view this space-time as embedded in a 5-dimensional Minkowski world governed by the following hypersurface equation. Yeah, so this is 5D Minkowski, and I want this hypersurface inside of 5D Minkowski, and the metric induced on this hypersurface maybe that's a homework problem. It can be shown fairly straightforwardly to be de Sitter. And from this point of view, we can already anticipate something rather immediately, which is that since the hypersurface equation in the embedding space that gives rise to de Sitter preserves a particular subgroup of the Poincare symmetries of 5D Minkowski, yeah, we can anticipate already what the isometry algebra of the space-time is. Yeah? Now, question. What subgroup of the 5-dimensional Poincare algebra does this hypersurface preserve? SO1,4. It preserves the 5-dimensional Lorentz transformations because of its structure, minus plus. Yeah? Now, I don't know if you're hardcore group theorists, but if you want, we can consider only the component that's continuously connected to the identity and is orthochronous and has positive determinant. If that's your thing, we do it that way. All good. I'm with you. If you're a fermion people, there's a double cover to this group that's simply connected and very beautiful. That's called spin 1,4. All good. I'm your people. We can do that too. Or we can think of it just at the level of the Lie algebra. But anyways, these are the isometries of the space-time. And how many are there? Oh yeah. So there's 10, which is the same number as the number of Poincare generators in 4-dimensional Minkowski space, or the number of generators of 4-dimensional ADS, which is SO3,2. Yeah? And so it's a maximally symmetric space-time indeed. Okay? And so this is our friend. Okay? And so what replaces the statement that this is a vacuum space, because it's not a space with time translation symmetries, is that it's a space, the unique space that admits the maximal number of isometries. SO4,1. Not a bad group. Nice group. In the bigger picture, nice group. Non-compact, but that's okay. Okay, non-compact Lie group. And I'd like to say, we'll come back to this group. Yeah, of course, for d-dimensional de Sitter, you can anticipate that the isometry algebra or the isometry group is SOD,1. Yeah, so for instance, 2-dimensional de Sitter, which is sometimes a useful toy model to have in mind, is SO2, 1, which at the level of the Lie algebras is isomorphic to SL2R. Nice group, a group that we're familiar with. The isometry group of the S3 is SO3, 1, which ironically is the Lorentz group in 4 dimensions, and so forth and so forth. Okay. And now let me say a comment about the causal structure of the space-time. Let me gather my thoughts. Isometries. Well, actually, no. Let me say a few more things about the isometries, and I'll use a colored chalk. So, some more properties of this Lie group. What is the maximally compact subgroup of SO14? So that's SO4, yeah? So we have a maximally compact subgroup, which is itself quite large. And in fact, this is manifested quite explicitly because it's the isometry algebra of the 3-sphere over here. Yeah? So that makes explicit, this coordinate system makes manifest the SO4 subgroup of SO41. Yeah? But of course, it also has other subgroups, many subgroups. This one over here makes manifest R3, an R3 subgroup of SO4, 1. And more than that, actually, it's ISO3. It's the rotations and translations of 3D flat. Yeah. But there's another one that this one makes manifest, which is a, yeah, can anyone identify another killing vector in this space? It's a little less manifest, but sufficiently manifest, I think, to be identified in 18 seconds. Good. So if we take x to lambda x and t to shift by, well, something like 1/2 log lambda or something like that. Yeah? Okay. This metric will remain invariant. And so there's a dilation symmetry. And in fact, that, which is less obvious, is an SO1, 1 subgroup of SO1, 4, that generator. Yeah? Yeah. Okay. And then, well, there's another one. Why not? I love this game. What are the isometries of H3? Oh yeah. What? Any takers? Well, let me not make you suffer. It's SO3, 1, which is, of course, a subgroup of SO4, 1 also. Yeah. So these different coordinates are a mosaic of different subgroups of the Lie algebra. Of course, none of them make the full isometry group manifest. Yeah. And another geometric feature that will play a prominent role in what follows is, but I'll anticipate it already, because I think it's, well, it may play a very important role later on, is the Euclidean continuation of this space-time. So in Euclidean signature, I'll make a comment now and we'll revisit this later. In Euclidean signature, we would have a positive curvature, maximally symmetric Euclidean Riemannian space, which is La Esfera. Excellent. The 4-sphere. The standard round metric on S4. Yeah? So the Euclidean version of this infinitely expanding Lorentzian universe is a compact 4-manifold, which is quite curious. We'll come back to that. That's an important point, I think. Okay, causal structure. So for the causal structure, it's very convenient to go to a coordinate system that brings everything to finite ranges, all of the coordinates to finite ranges. Yeah? And what one can do, say we want the causal structure of the global space, we can pull out this cosh squared t, yeah, and we have this thing over here times an S3, okay? And now we can define a coordinate t as equal to dt over cosh t, yeah, okay, which I leave as a homework problem. I think it's some inverse trigonometric function. And but the resulting metric in that coordinate is given by and let me shift the time as follows. Oops. The following metric, which in other words says that the global de Sitter is conformally equivalent to the Einstein static universe, yeah, except for one small detail, which is that the range of t we will take to go between minus pi to 0. Okay? So the infinite past and the infinite future have been compacted into this finite range coordinate t. Yeah? And what we see is that, sorry, I think in my conventions later, let me write it like this. So the beginning of the world is at t equals 0, and the end of the world is at t equals pi. And we see this characteristic feature in these conformal coordinates that we have a double pole as we approach the infinite past or the infinite future, yeah? So it's a double pole structure. And now we have equipped ourselves with enough information to draw the Penrose diagram of the space-time. Yeah. So that's a square, yeah, where t goes from 0 to pi. This slice over here is an S3, and the poles of the S3 rest along these vertical lines, yeah. And every point along this S3 is an S2, yeah, that grows and then shrinks to form the three-sphere, yeah. And so the Penrose diagram is a square. And now we see very clearly, as we evolve in our little world line or world tube, our cosmological observatory, yeah, that if we draw past light cones of our experience, there will always, even if we are an eternal observatory that lives forever, for all the way to the future infinity, yeah, this is a globally, geodesically complete space. This is it. This is the beginning and end of the universe. There will always be matters of the universe that occur, for instance, an exploding star, yeah, in such a way that they are forever out of causal contact from the observatory, yeah? So this goes back to this cosmological event horizon. And this is a feature that many FLRW spaces exhibit, like we said before, and certainly one that is exhibited in this attractor cosmology of the de Sitter. Yeah? So are there any questions about this? So this is an important feature because it means that there's something already that the space-time has in common, at least naively, and I emphasize that, to the black hole. Yeah? Regions of space-time that are out of causal contact forever from a quasi-local observer. Okay? And if our world continues, and if lambda persists, the situation that we will find in. We will be surrounded by a cosmological horizon whose size is this 20 billion light years figure. And the light will become redshifted and eventually more redshifted, and they just fall through the horizon. We will not be able to see physics beyond the horizon. That's the deal. Yeah. Okay. Any questions? So that's the causal structure. And these are the most symmetric configurations. And I guess at this point I should write one more coordinate system, which is actually the coordinate system that was first written down in 1917 by de Sitter himself during discussions with Einstein about whether or not we can have a purely static, stable universe. Ironically, the discovery of this spacetime was to make the case that this is a static, that Einstein's theories admit static universes. It's another nice paper to read. 1917, roughly the same year when Schwarzschild discovered his solution, yeah, in the trenches. And so this coordinate system, which sometimes is known as the static patch of the de Sitter space-time, has the following, and here I'll reinstate units. Schwarzschild-like behavior. Let me write it in two different coordinate systems because sometimes I find myself liking more one than the other. Okay? So you see that this is a coordinate system where R ranges from 0 to L. This is the standard metric on S2. And this is another time coordinate, yeah, which looks like a purely static spacetime. A macroscopic portion of the spacetime can be expressed in a completely static form, like the exterior of a black hole horizon. Yeah? And what it covers, this coordinate system, is the overlap between the past light cone of a future and the future light cone of the past point of an eternal world line. Yeah? It's this region over here. And let me exemplify the different. So constant R slices go along these curves over here. Yeah. And constant T slices are these curves over here. Yeah. And as R tends to 1, we have a future and a past event horizon because we have an infinite redshift surface at R is equal to L. Okay? And so we have this cosmological event horizon or de Sitter horizon that from the static point of view is this infinite redshift surface. And that's why events that emit light, if you have an event that emits light, the light looks increasingly redshifted. Yeah? And so what happens from the static patch point of view is that instead of having a very time-dependent description of the space-time, all of that time dependence is subsumed into the behavior, the redshift patterns due to the event horizon itself. Okay? Just like if you wanted to describe a Schwarzschild black hole both within and outside the horizon, you would have to deal with a time-dependent coordinate system. Yeah. Good. So that's the static patch. And this T over here is also an SO1,1 subgroup. Yeah? Now, how are we doing for time? And now is a natural point to break the lecture. And then we meet again. So what? Go on.
Let's thank
Oh,
you.
yeah, thank you. Yeah.
More questions?
Okay, thanks for the lecture.